In the darkest hours of the Second World War, the fate of nations hung by a thread across the cold, unforgiving waters of the Atlantic Ocean. Great Britain, standing defiant against the Axis powers, was an island fortress, but a fortress that depended entirely on a constant flow of food, fuel, and the instruments of war from across the sea. From 1939, this vital lifeline was under relentless assault. German U-boats, hunting in wolf packs, stalked the convoys, turning the ocean into a graveyard of steel. In the first year and a half of the war, Britain lost over 4 million tons of merchant shipping. The attrition was unsustainable. British shipyards, under constant threat of air attack, could not replace the losses fast enough. For every new ship they launched, 2 were being sent to the bottom. A solution had to be found, and it had to be found quickly, or the war would be lost. The answer would not come from traditional methods. It would come from an unprecedented feat of industrial will, a program that would see the United States, not yet officially in the war, turn its manufacturing might to the sea. It was a plan to build ships faster than the enemy could sink them. These ships wouldn't be pretty. They wouldn't be fast. But they would be built in their thousands. They were the Liberty ships, the simple, slow, and utterly essential vessels that formed the backbone of the Allied victory. In 1940, with much of Europe under Axis control, the Battle of the Atlantic was a battle of logistics. Winston Churchill knew that Britain's survival depended on maintaining control of the sea lanes. He reached out to his American counterpart, President Franklin D. Roosevelt. The United States was officially neutral, but Roosevelt was determined to aid the Allied cause. He declared the nation would become the arsenal of democracy. This commitment began with programs like Lend-Lease, but it soon became clear that the weapons and supplies were useless if they couldn't cross the ocean. The problem was twofold: a severe shortage of ships and a German submarine campaign that was brutally effective. Admiral Karl Donitz's U-boats were sinking Allied merchant vessels at catastrophic rate. The convoy system, where merchant ships traveled in groups protected by naval escorts, offered some defense. But the vastness of the Atlantic and the limited number of warships meant that even protected convoys were vulnerable. A single convoy, like ONS-5 in May 1943, could become a scene of carnage, with dozens of ships lost in a running battle that lasted for days. This was a simple, brutal equation of replacement. The Allies had to build ships faster than the U-boats could sink them. In late 1940, Britain placed an urgent order with the United States for 60 new cargo ships. But 60 ships would be a drop in the ocean. The scale of the crisis demanded a radical rethinking of shipbuilding itself. The man tasked with overseeing this monumental effort was Admiral Emory S. Land, head of the U.S. Maritime Commission. The Maritime Commission had been established in 1936 to restore the nation's merchant marine, but the war in Europe transformed its mission. In early 1941, President Roosevelt announced the Emergency Shipbuilding Program, calling for construction of 200 new ships. This was just the beginning. The program would eventually expand to become the largest shipbuilding effort in human history, a key component of a strategy based on overwhelming the enemy with sheer industrial output. The challenge was immense. At the time, the United States had a limited number of shipyards capable of building ocean-going vessels, and most were already occupied with naval contracts. To meet the demand, new yards would have to be built from scratch, and they needed a design, not for a state-of-the-art vessel, but for a simple, cheap, and quick-to-build cargo carrier, a ship that could be mass-produced by a workforce that had never seen a shipyard before. The foundation for this emergency vessel came from the very nation it was meant to save. The British had designed a simple tramp steamer, the Ocean Class, based on an 1879 model. It was old, slow, and technologically obsolete, but was proven and, most importantly, easy to build. The U.S. Maritime Commission took the British Ocean-class design and adapted it for American production methods. The goal was to replace riveting, a time-consuming and skill-intensive process, with welding. This was a revolutionary step for shipbuilding on this scale. The design was designated EC-2SC1. EC for emergency cargo, 2 for its large size, S for its steam engine, and C1 for the specific design type. It was a vessel just over 441 feet long, capable of carrying over 10,000 tons of cargo. Its power came from a triple expansion steam engine, a design that was considered obsolete but was chosen because it could be manufactured by companies with no marine engine experience, like locomotive builders. Everything about the ship was optimized for mass production. President Roosevelt initially referred to the new ships as dreadful-looking objects, and a Time magazine article dubbed them ugly ducklings. The name that stuck, however, came from Admiral Land. On the day the first ship was launched, he declared the fleet would bring liberty to Europe, and so they became the Liberty ships. The first of these, the SS Patrick Henry, was launched on September 27, 1941, a day that was declared Liberty Fleet Day. 14 ships were launched on that single day from yards across the country. The attack on Pearl Harbor just a few months later, in December 1941, removed any remaining constraints on the program. The initial order for 200 ships ballooned. The demand for shipping was now astronomical, not just for the Atlantic, but for a new, sprawling war in the Pacific. To build these thousands of ships, an entirely new industrial infrastructure was needed. The Maritime Commission partnered with established companies and new consortiums to create shipyards specifically for the Emergency Program. These yards were built at breathtaking speed on what had been mudflats and empty coastline. They were not traditional shipyards, but vast assembly plants, designed and ground up for a new way of building. The most famous and productive of these new operations were run by one man, a charismatic industrialist with no prior shipbuilding experience named Henry J. Kaiser. Kaiser had made his name building massive public works projects like the Hoover and Grand Coulee dams. He was a master of logistics, organization, and most importantly, of motivating a workforce to achieve the impossible. He applied the same principles of large-scale construction to shipbuilding. His yards, like the ones in Richmond, California, and Portland, Oregon, became legendary for their efficiency and staggering output. Kaiser's key innovation was his relentless focus on prefabrication. Instead of building a ship piece by piece on the slipway, his yards built enormous sections, double bottoms, deck houses, bow assemblies, in specialized workshops. These modules, some weighing over 200 tons, were then carried by massive cranes and welded together on the slipway, like assembling a giant puzzle. This dramatically reduced the time a ship spent occupying a valuable building berth. This assembly line approach, combined with the widespread use of welding instead of riveting, was the secret to the Liberty ship's incredible production speed. It was a revolution that would change shipbuilding forever. The methods pioneered by industrialists like Henry Kaiser transformed shipbuilding from a craft into a mass production industry. The results were nothing short of miraculous. In 1941, the average time to build a Liberty ship, from laying the keel to launch, was about 230 days. By the end of 1942, that time had plummeted. Across all 18 emergency shipyards, the average construction time was just 42 days. The shipyards were no longer just building ships. They were launching them at a rate the world had never seen. This incredible acceleration was made possible by a new army of labor. With millions of men serving in the armed forces, the shipyards turned to people who had been previously excluded from heavy industry. Hundreds of thousands of women, famously personified by Rosie the Riveter, took on jobs as welders, crane operators, and electricians. They were joined by African Americans migrating from the South and others who had never imagined working in such an environment. These were not skilled shipwrights. They were former farmers, shopkeepers, and homemakers. The genius of the system was its simplicity. The process was broken down into smaller, repetitive tasks that could be learned quickly. A worker might spend the entire war welding one specific type of seam, and they became an expert at it. The Kaiser shipyards in particular became magnets for workers from across the country, with some yards employing nearly 100,000 people at their peak. They operated 24 hours a day, 7 days a week. The noise of riveting hammers and the bright flash of welding arcs never ceased. The drive for speed became a point of national pride and a fierce competition between the shipyards. Henry Kaiser, a master of public relations, decided to stage a demonstration that would capture the world's attention. In November 1942, his Richmond, California shipyard set out to build a Liberty ship from start to finish in record time. The ship was the SS Robert E. Peary. The keel was laid on a Sunday morning. Using prefabricated sections that had been prepared in advance, an army of workers swarmed the slipway. The process was meticulously choreographed. As one team finished welding a section, another was already moving the next piece into place. Reporters and newsreel cameras watched in astonishment as the ship took shape before their eyes. The hull, the superstructure, the funnel, the masts, all were lifted and welded into place with stunning speed. Just 4 days, 15 hours, and 29 minutes after the first piece of steel was laid, the SS Robert E. Peary slid into the water. It was a fully functional ship, and it was launched faster than many vessels could be repaired. While this was a publicity stunt that wasn't representative of normal production, it was a powerful symbol of America's industrial capability. The message to the Axis powers was clear. You cannot sink them fast enough. By 1943, the Liberty ship program was at its peak, launching an average of 3 ships every single day. The tide in the Battle of the Atlantic was beginning to turn, not just through better naval tactics, but through the sheer weight of numbers. In total, from 1941 to 1945, American shipyards produced 2,710 Liberty ships. It remains the largest class of ships ever built to a single design. So what were these ships that carried the Allied war effort on their backs? The ugly duckling, nickname was fitting. They were the opposite of sleek. Their design was purely functional, almost brutally so. They had a single, straight-rake bow and a cruiser stern. A simple, boxy superstructure sat amidships, with the engine room below. The rest of the deck was dominated by 5 cargo holds, 3 forward of the superstructure and 2 aft. Each hold was served by booms and winches, allowing the ship to load and unload its own cargo in primitive ports. That cargo could be anything and everything the war required. Tanks, trucks, ammunition, created aircraft, food, fuel drums, and raw materials. They were armed for self-defense, typically with a 4-inch or 5-inch gun on the stern for use against surface submarines, and a number of smaller anti-aircraft guns. But their best defense was simply to avoid being hit. Their slow speed of 11 knots was a major liability. It meant they couldn't outrun a surface U-boat, and often struggled to keep up with faster naval convoys. They were, in essence, sitting ducks. This was all part of the design philosophy. The Liberty ship was a disposable asset and expendable. The Maritime Commission specified a 5-year design life. They were built to do a job, survive if they could, but be sacrificed if necessary. The men who sailed them, the merchant mariners, knew this. They sailed into the most dangerous waters of the war on slow, vulnerable ships, with casualty rates higher than any branch of the U.S. Armed Forces. These ships and the crews who manned them became the lifeline of the Allies. They carried 2/3 of all cargo shipped out of the U.S. during the war. They supplied the invasion of North Africa, the brutal campaigns in Italy, and the D-Day landings in Normandy. In the Pacific, they served as supply vessels, troop transports, and even as makeshift aircraft repair depots. They were adapted for countless roles, becoming hospital ships, animal transports, and mobile barracks. The ugly ducklings were everywhere, the unglamorous but indispensable workhorses of a global conflict. Without them, the logistics of fighting a 2-front war would have been impossible. But the same production methods that allowed them to be built so quickly also concealed a hidden and sometimes fatal flaw. As these welded ships sailed from the warm waters of the Pacific into the frigid North Atlantic, a terrifying problem began to emerge. Ships were breaking apart. Sometimes it would sound like a gunshot. A crack would appear in a hull or deck. In the worst cases, entire vessels would split in 2, sinking in minutes with little warning. The very innovation that made the Liberty ship possible, its all-welded construction, was now under suspicion. The lifeline of the Allies had a secret vulnerability, one that engineers raced to understand before it caused a catastrophe. Before this hidden flaw became a crisis, the Liberty ships were proving their worth in the most dangerous environment on Earth, a wartime convoy. For the merchant mariners aboard, life was a mixture of monotonous routine and sudden, heart-stopping terror. A convoy could consist of 40, 60, or even more merchant ships, steaming in a vast grid of columns and rows. They were protected by a thin screen of naval escorts, destroyers, corvettes, and frigates that constantly circled the formation, hunting for the telltale sonar echo of a U-boat. The Liberty ships, with their slow 11-knot speed, often dictated the pace of the entire convoy. Keeping station was a constant challenge, especially in rough seas or fog. A ship that fell behind or strayed from its position became a straggler, an easy target for any lurking U-boat. Days were spent on watch, maintaining equipment, and staring out at the endless gray water. But at any moment, the calm could be shattered. An explosion, a pillar of smoke on the horizon, a frantic signal from an escort. It meant the wolf pack had found them. The Liberty ship SS Stephen Hopkins provides a dramatic example of the dangers. Sailing alone in the South Atlantic in September 1942, it was ambushed by the heavily armed German Commerce Raider Steer. Outgunned and on fire, the crew of the Stephen Hopkins fought back with their single 4-inch stern gun. In a short, brutal firefight, they scored direct hits on the German raider, damaging it so severely that its own crew had to scuttle it. The Stephen Hopkins went down, but it took its attacker with it. Most encounters were not so heroic. Around 200 Liberty ships were lost during the war to enemy action, the majority falling victim to U-boats. They were sunk by torpedoes, mines, and even air attacks. But the enemy wasn't the only thing that could destroy a Liberty ship. The first signs of trouble were dismissed as isolated incidents or poor workmanship. A crack would appear on deck after a storm. A well would fail in a minor way. But by the winter of 1942-43, the reports were becoming too frequent and too alarming to ignore. The problem was given a name: brittle fracture. Steel, normally a ductile material that bends and stretches before failing, was behaving like glass. Under the right conditions, it was shattering. The most dramatic and famous case occurred not in a raging storm, but on a calm, cold day in port. On January 16, 1943, the T-2 tanker SS Schenectady, a ship built with the same welded construction methods as the Liberties, was tied to a dock in Swan Island, Oregon, having just completed its sea trials. Without any warning, with a noise heard a mile away, the ship's hull and deck cracked completely through. The Schenectady broke its back, its bow and stern settling into the mud of the river bottom, leaving the midsection grotesquely buckled in the air. The event was a profound shock to engineers and naval architects. A brand new ship had torn itself apart in calm water, under no load. If it could happen here, it could happen to any of the thousands of welded ships now at sea. The cause had to be found, and fast. A board of investigation was convened. They discovered a perfect storm of contributing factors. The first was the welding itself. In a traditional riveted ship, the hull is made of thousands of overlapping plates fastened together. A crack in one plate would simply stop at the edge of that plate. But welding created a single, continuous, monolithic structure. If a crack started, there was nothing to stop it from running for hundreds of feet, right across the vessel. The second factor was stress. The rapid, assembly line construction and inexperienced welders sometimes led to microscopic flaws or sharp corners in design, like at the corners of the square cargo hatches. These acted as stress concentrators, creating a starting point for a fracture. The final, critical ingredient was temperature. The steel used for the Liberty ships had a tendency to become brittle in the cold. The frigid waters of the North Atlantic in winter could drop the hull's temperature to the point where the steel lost its ductility. A tiny flaw under stress. In cold steel, this was a recipe for disaster. The investigation found that nearly 1,500 significant brittle fractures were recorded across the Liberty fleet during the war. In total, 12 ships, including 3 Liberty ships, broke completely in half without warning. The problem was real, and it threatened to undermine the entire Emergency Shipbuilding Program. A full-scale recall was impossible. The ships were needed for the war effort. The solution had to be a retrofit that could be applied quickly to ships in service. The answer was elegantly simple: the crack arrestor. Since the problem was that cracks had nothing to stop them, engineers reintroduced the logic of a riveted ship. A thick strap of steel was riveted onto the deck and hull, running lengthwise. If a crack started, it would run into this riveted seam and stop, preventing a catastrophic failure. Other fixes were implemented. The sharp corners of the hatches were rounded to reduce stress concentration. Welding procedures were improved, and welders received better training and inspection. These measures, known as strapping, were effective. While minor cracks still occurred, the catastrophic losses due to brittle fracture ceased. The Liberty ships could continue their vital work. The investigation into the Liberty ship failures had a profound and lasting impact on engineering and metallurgy. It led to a much deeper understanding of fracture mechanics and the importance of steel quality for welded structures, lessons that informed the design of ships, bridges, and pipelines for decades to come. But even as the Liberty ships were being patched and reinforced, the Maritime Commission was already looking ahead. The ugly duckling had done its job, but the war now demanded a ship that was not just numerous, but faster and stronger. The successor was already on the drawing board. The Liberty ship was a brilliant emergency measure, a blunt instrument designed for a desperate time. But by 1943, the strategic situation had changed. The Allies were on the offensive, and the nature of naval warfare, particularly in the vast Pacific theater, demanded more than just numbers. It demanded speed. The Liberty's 11-knot speed was a constant tactical problem. It made the ships easy prey for a new generation of faster German U-boats and forced naval convoys to travel at a crawl. In the Pacific, where distances were immense, that slow speed was a logistical nightmare, delaying the arrival of critical supplies for island-hopping campaigns. The U.S. Maritime Commission had anticipated this need as early as 1942. They began planning for a successor, a ship that could retain the mass production benefits of the Liberty program, but with significantly better performance. This new design was a VC-2, the Victory ship. The design goals were clear: create a vessel capable of 15 to 17 knots, making it fast enough to outrun most submarines and travel with military convoys. It also needed to be stronger and more durable, incorporating the hard-won lessons from the Liberty ship's structural failures. The most significant upgrade was the power plant. The obsolete triple expansion steam engine of the Liberty was replaced in most Victory ships with modern, powerful steam turbines, the same kind used in destroyers. These engines, originally intended for the Lend-Lease program, generated between 6,000 and 8,500 horsepower, more than double that of the Liberty. A smaller number of Victory ships were fitted with powerful diesel engines, while a handful of early models, facing a shortage of turbines, were equipped with the old Liberty-style steam engines as a stopgap. These different engine types led to different designators, like AP2 for the standard turbine, or AP3 for the triple expansion engine. To handle the higher speeds, the hull was completely redesigned. The Liberty's simple, boxy shape was replaced with a more elegant form featuring a sharply raked, flare bow and a classic cruiser stern. This improved hull was more efficient, cutting through the water with less resistance. The design also directly addressed the brittle fracture problem. Stronger steel was used in key areas. The sharp, square corners on hatches and other openings were replaced with rounded ones to eliminate stress points. Crucially, while the ships were still primarily welded, designers incorporated riveted seams at the shear strake, where the deck meets the hull, to act as built-in crack arresters. The Victory ship was designed from the keel up to be more resilient. This more complex design meant a Victory ship could not be built as quickly as a Liberty, but the production system was now a well-oiled machine. The same shipyards, including Kaiser's facilities in Richmond and Oregon, switched over producing the new type. The first Victory ship, the SS United Victory, was launched in the Oregon Shipbuilding Corporation yard on January 12, 1944. Over the next year and a half, production ramped up, running in parallel with the continued, though reduced, construction of Liberty ships. In total, 531 Victory ships were completed. While this was only a fraction of the 2,710 Liberties built, their arrival was perfectly timed for the final, decisive phase of the war. By 1944, the Battle of the Atlantic had largely been won. The primary theater for these new, fast cargo ships was the Pacific. Their speed made them ideal for supporting the fast carrier task forces of the U.S. Navy, which could not afford to be slowed down by 11-knot supply ships. Victory ships delivered the vast quantities of ammunition, fuel, and food needed for the invasions of Iwo Jima and Okinawa. They could make independent voyages without an escort, a risk that was rarely taken with liberty, freeing up warships for combat duty. A significant portion of the Victory fleet was built not as cargo carriers, but as dedicated attack transports. These were the AP-5 variant, known as the Haskell class. They were operated by the Navy and designed to carry over 1,500 troops and the landing craft needed to get them ashore. Ships like the SS Red Oak Victory, built in the Richmond shipyards, were designated as attack transports and loaded with ammunition for the Pacific Fleet. They were a direct link between the home front factories and the frontline fighting. The Victory ship was, in every respect, a superior vessel to the Liberty. It was faster, stronger, safer, and more economical to operate. It represented the evolution of emergency shipbuilding, moving from pure quantity to a balance of quantity and quality. However, the Victory ship's design life was still that of a mass-produced emergency vessel, like the Liberties. Many were built using asbestos for insulation around pipes and boilers, a hidden danger that would affect shipyard workers and crew members for decades to come. As the war in Europe ended in May 1945, and the war in the Pacific drew to its sudden close in August, America found itself in possession of a staggering number of ships. Thousands of Liberties and hundreds of brand-new Victory ships, their wartime mission complete, now bobbed at anchor in ports across the country. The question was what to do with this vast, sudden surplus. The ships that had been the key to winning the war now represented a colossal challenge of peacetime conversion and disposal. Their next chapter would see them play a vital, but very different, role in shaping the post-war world. With the surrender of Japan in August 1945, the world fell silent after 6 years of brutal conflict. The United States, which had entered the war with a modest merchant marine, now controlled a fleet of more than 5,000 ships. The majority of these were the Liberties and Victories, the fruits of the Emergency Shipbuilding Program. This vast armada had been built for a single purpose: to win the war. Now, in peace, it presented a complex problem. Allowing thousands of government-owned ships to flood the commercial market could crash shipping rates and bankrupt private American shipping companies. At the same time, the world was in desperate need of shipping. Allied nations whose merchant fleets had been devastated by the war needed vessels to carry food, raw materials, and finished goods to rebuild their shattered economies. The solution came in the form of the Merchant Ship Sales Act of 1946. This legislation created an orderly process for the U.S. government to sell off its surplus wartime ships. American citizens and companies had priority, followed by foreign buyers. The two classes of ships, Liberty and Victory, met very different fates in this new commercial marketplace. The Liberty ships, with their slow speed and outdated engines, were less attractive. They were cheap, however, and available in huge numbers. Hundreds were sold to Greek, Italian, and other European shipping magnates. For a relatively small investment, they could acquire a vessel capable of carrying 10,000 tons of cargo anywhere in the world. These sales were instrumental in rebuilding the merchant fleets of America's allies. For a brief period in the late 1940s and early 1950s, the Liberty ship became the quintessential tramp steamer, plying the world's oceans carrying bulk cargoes like grain, coal, and ore. They were the slow, steady workhorses of post-war recovery, just as they had been for the war effort. But their obsolescence was undeniable. As shipbuilding nations like Japan and Germany recovered, they began producing new, faster, and more fuel-efficient diesel-powered vessels. The steam-powered Liberties simply couldn't compete. By the mid-1950s, they were already being sold for scrap in large numbers. The Victory ships, on the other hand, were a much hotter commodity. Their 15-knot speed and more modern turbine engines made them far more desirable for liner services and more competitive routes. American shipping lines bought many of the best Victory ships, which went on to form the backbone of the U.S. Merchant Marine for the next 2 decades. They were reliable, versatile, and well-suited for a wide range of cargo. Not all the ships were sold. The Ship Sales Act also provided for creation of a strategic reserve. Hundreds of the best-maintained Liberties and Victories were designated for the National Defense Reserve Fleet. These vessels were taken to sheltered anchorages, like Sassoon Bay in California or the James River in Virginia, and put into long-term preservation. This mothball fleet was a floating insurance policy, a reserve of shipping that could be reactivated in a future national emergency. The wisdom of this policy was proven just a few years later. With the outbreak of the Korean War in 1950, there was a sudden, massive demand for shipping to supply UN forces. Over 100 Liberty ships were pulled from the mothball fleet, rapidly recrewed, and sent to the Pacific. Once again, the ugly ducklings were called upon to serve as a military lifeline. After the conflict, most were returned to storage. Their brief return to service a final echo of their wartime glory. A decade later, during the Vietnam War, it was the Victory ships' turn. Their higher speed was essential for supplying the distant conflict. From 1965 to 1970, 172 Victory ships were reactivated from a reserve fleet and put into service, many making repeated voyages across the Pacific. By the 1970s, however, the era of the emergency ships was well and truly over. The rise of containerization and the development of massive, specialized bulk carriers and tankers rendered them obsolete. The remaining ships in the reserve fleets were old, expensive to maintain, and no longer militarily useful. One by one, the silent residents of the mothball fleets were towed away to scrap yards in the U.S. and abroad. The sound of cutting torches replaced the flash of welders' arcs as the ships that had been built in a matter of days were painstakingly dismantled over weeks. By the 1980s and 90s, a fleet that once numbered in the thousands had dwindled to just a handful. It became clear that if something wasn't done, the physical memory of this incredible chapter in industrial and maritime history would vanish completely. The ships that had been designed to be expendable, built to last only 5 years, had in many cases served for 30 or 40. They had won a war, rebuilt a continent, and served in 2 more conflicts. Now, a new mission emerged to save the last few survivors as a tribute to the millions who built them and sailed them. Out of the more than 3,200 Liberty and Victory ships built, a fleet that bridged the oceans and carried victory on its back. Only a tiny handful escaped the scrapyard. Today, just 5 remain in the United States as floating museums, preserved by the tireless efforts of volunteers dedicated to keeping their stories alive. 2 of these are Liberty ships, the ugly ducklings that started it all. Both are maintained in operational condition, a remarkable feat of preservation for vessels designed to last only 5 years. In Baltimore, Maryland, rests the SS John W. Brown. Built in 1942, she is a veteran of the Atlantic convoys and invasions of Italy and southern France. Today, she serves as a living classroom and a memorial to the merchant mariners and naval armed guard who served aboard her. On the West Coast in San Francisco is the SS Jeremiah O'Brien. She is a pristine example of a late production Liberty, and famously, she is the only one of the thousands of ships that stormed the beaches of Normandy to have survived. In 1994, on the 50th anniversary of D-Day, the O'Brien, powered by her original triple expansion steam engine, crossed the Atlantic under her own power to participate in the ceremonies. It was a poignant tribute to the thousands of ships that made the invasion possible. 3 Victory ships also survive, each representing a different aspect of the type's service. In Tampa, Florida, the SS American Victory is preserved in operational condition. She is a veteran of the final days of the Pacific War and later served in both the Korean and Vietnam conflicts. In San Pedro, California, the SS Lane Victory serves as a museum and memorial. She too saw service in 3 wars and for many years offered cruises, giving the public a chance to experience the sights and sound of a World War II-era steamship at sea. And in Richmond, California, in the very shipyard where she was built by Henry Kaiser's workforce in 1945, sits the SS Red Oak Victory. She was built as an ammunition carrier and served in the final year of the war, a direct product of the industrial might she now commemorates. These 5 ships are more than just steel and steam. They are tangible links to a time when an entire nation mobilized to achieve a single goal. The legacy of the program they represent is immense and multifaceted. Militarily, the emergency fleet was a foundation of Allied logistics. Without this bridge of ships, it is difficult to imagine how Great Britain could have survived, how the Soviet Union could have been supplied, or how the United States could have projected its power across 2 oceans. Industrially, the program was a revolution. The techniques of prefabrication and mass welding, refined in the emergency shipyards, became standard practice in post-war construction. The program proved that with enough will and organization, production could be scaled to almost any challenge. Scientifically, the painful lessons learned from the brittle fractures of the Liberty ships led to a new field of science, fracture mechanics. The understanding gained from those failures made everything from bridges to pipelines to modern ships safer and more reliable. And socially, the shipyards were a catalyst for change, opening doors in heavy industry for women and minorities on a scale never seen before, and accelerating the migration of workers across the country. The story of the Liberty and Victory ships is a story of logistics, steel, and engineering. But above all, it is a human story. It is the story of designers given an impossible task, of industrialists who redefined the meaning of mass production, of hundreds of thousands of ordinary citizens who built the ships, and of the merchant mariners who sailed them into harm's way. They were called ugly ducklings, built to be expendable. But these simple ships became the lifeline of a world at war, a symbol of industrial resolve, and a testament to the idea that in a time of crisis, ordinary people can achieve the extraordinary.